Bateman's polynomials for the powers of the odd integers. Plain honesty, simple truth, easy understanding. The joy of finding things out for yourself. Even if you are only a minority of one, the truth is the truth. Mahatma Gandhi. We can subdivide an odd integer into its two parts, n plus 1 and n, and derive the two adjacent triangular numbers, triangular number of odd rank, 2n plus 1 times n plus 1, and triangular number of even rank, 2n plus 1 times n. Now, triangular number of odd rank squared minus triangular number of even rank squared is equal to 2n plus 1 cubed, due to the fact that the partial sums of the cubes always add to give a triangular number squared. This is an embarrassment to mathematicians who turn a blind eye to it because it undermines the credibility of their procrastinations with regard to Fermat's last theorem. What we have is the difference of two squares alias the simpleton proof of Fermat's last theorem, which applies to every cube of every integer from integer equals 1 to integer equals integer plus 1 without end. All we have to do is multiply through the difference of squares expressions for the cubes repeatedly by the cube root squared, and we will have a difference of square expressions for every odd power x, from x equals 5 to x equals x plus 2, without end for all integers, all of which is irrefutable verification of the simpleton proof of Fermat's last theorem. If we square the triangular number of odd rank, we get a polynomial expression. If we square the triangular number of even rank, we get another but different polynomial expression. We then subtract the even polynomial from the odd one to get a third polynomial, highlighted blue, that outputs 2n plus 1 cubed when the input to the polynomial is n. All we have to do then is multiply the resultant polynomial by 2n plus 1 to get a new polynomial which outputs 2n plus 1 to the fourth power for an input of n. We multiply the new polynomial by 2n plus 1 to get yet another polynomial that outputs 2n plus 1 to the fifth power for an input of n. All we have to do then is repeat step 5 indefinitely to give, voila, Bateman polynomials up to the power 10 and beyond. Like the polynomials resulting from a plus b raised to a power x, there are x plus 1 terms. The relative magnitude of the coefficients between a Bateman polynomial and one due to the binomial expansion of a plus b raised to a power x is given by the quotient of 3 to the power of x divided by 2 to the power of x, which is approximately 57 for a power of 10. The difference is compensated for by numerically smaller values for the power terms of n compared to those of the product of power terms of a and b. The following statements apply to Bateman polynomials. For all equations, the coefficients add up to give 3 to the power x, where x is the largest power of the polynomial. If we alternate the signs of the equations, plus, minus, etc., then we output 2n minus 1 to the power x. Hence, 2n minus 1 all cubed equals 8n cubed minus 12n squared plus 6n minus 1. The positive coefficients sum to 3 to the power x plus 1 all divided by 2, and the negative coefficients sum to 3 to the power x minus 1 divided by 2. We obtain the difference of powers for two odd integers as shown using n1, n2 as the inputs for the cubic polynomials. Hence, 2n1 plus 1 all cubed minus 2n2 plus 1 all cubed is equal to n1 cubed minus n2 cubed all multiplied by 8 plus n1 squared minus n2 squared all multiplied by 12 plus n1 minus n2 all multiplied by 6. Finally, we should add that the difference of squares of the triangular numbers output the cubes of every integer, odd or even, but only upscale to an odd power. Bateman polynomials only output powers for the odd integers, but upscale progressively to give both odd and even powers. QED